So speaking of going from there, we have the concept called standard deviation, right? Measures of variation. They fall into a bunch of different categories, but the important one is standard deviation. All right, that's what I was talking about before when I said, if I tell you that the class average on a test was 80, you say that's meaningless. And I say I agree, because it doesn't tell you what you got on the individual level. It doesn't really tell us how the class did as a whole. All right. If I tell you that the mean is 50 and the measure of spread, which we're calling standard deviation, is 0, then you know what everybody got. Right? If I tell you that the class average is a 50, which is not good, but the standard deviation, the measure of how spread out the data are, was, let's say, also 50, then that tells us that the data is very widely spread out. On an individual level, that equals hope. Because if you studied for that test, you know you prepared, you're like, well, I'm gonna be a deviation from the mean on the high side, because I didn't find that test difficult at all. We've all walked out of the classroom, sometimes on the long end and sometimes on the short end, where people are like, that test was so freaking hard, and they're not even being that polite. And then other people are like, I don't know what you're talking about. It wasn't that bad. I thought it was easy. And you're like, you shut up. Just failed it. Studied all night. You know, it all kind of balances out in the end, because the next week you're on the opposite end of it, where you're like, oh, I got 100 on that one. Oh, you're not talking now, are you? You know, so but it has to do with the standard deviation, because you don't know how everybody else compares to you with just the mean. All right? And you don't know how everybody compares to each other with just the mean. All right? So what we do is we figure out a number that represents the spread of the data. Right? If that number is very small, if it's close to 0, it means the data is very tightly packed. If the standard deviation is very large, it means the data is more loosely organized. Right? So when I'm dealing with two separate sets of data, it's very easy to see which data set is more tightly organized and which one is more loosely organized. Right? Because one will have a smaller standard deviation than the other. All right? So that's kind of nice. The problem is, one data set all by itself, you get a standard deviation and be like, I don't know, is this a good one or a bad one? Standard deviation is very comparative. Right? It's not very meaningful unless you have something else to compare it to. Right? Aside from the fact that smaller is better. Right? Context is a very important driving factor behind a lot of this stuff, because, you know, like, if you're talking about medicine, you know, like if you work in medical research and you're trying to develop a new drug that will regulate I was going to say heart rate, but I'll keep it simple, blood pressure. You know, like you don't want a large variation. You want it to actually be able to do what you're saying it's going to do, right? So it's going to reduce your blood pressure by whatever, give or take. Right? That give or take is your standard deviation. All right? You want that give or take to be small. You want it to be very, very predictable. All right? That's the power of this particular idea. I mean, we can go a little bit more simplistic with, I mean, the classic examples are, you know, like 10 bags of M&Ms are randomly selected and weighed. The stated weight by the company is that it should be this amount, but when you collect the data, the weights were this and that and the other thing. You know, is the company telling the truth, or are they full of crap? You know, that's fine too. There's a lot of value in that sort of thing, but that's just getting a quick look at it. It doesn't really get across the idea of the power of the concept. I do it with gas mileage. Right? It's probably kind of a little too nerdy, but I want to see what the variation is in my gas mileage based off of my driving. All right, so I'll fill up my tank, and I'll collect the gas mileage after the next fill up, taking note of what the conditions were in which I was driving. Right? Is it aggressive driving? Is it long driving? Is it commuting? Because the kids got hockey tournaments that are 3 hours away. That's highway, and I got to commute to work. What's the variation? I normally get around 32 miles per gallon, give or take. What's the give or take when I'm commuting, and what's the give or take when I'm long driving? Right? When I'm long driving, I can tell you, just based off of empirical evidence, data collected in the nerdiest fashion possible, that much. Yeah, it's 33 miles per gallon, give or take 0.25 mpg. All right, pretty spot on. Commute to work all over the place. And it's a function of whether I'm running late. That's exactly it. So the data was so inconsistent I couldn't draw any meaningful conclusions. But long driving, pretty spot on. Right? And so that becomes predictable. Like now you can start planning things. On a larger scale, now you can start thinking about, like, for example, if you're in the airline industry, if you know what the average fuel consumption is going to be, give or take, with a small give or take, now you can set the rates for the flights. So if you've seen flight costs become more consistent over the years, it's because and it is, believe it or not, it is more consistent. It's just consistently high. It is because they have a better handle on the fuel consumption now. Right? So how do you compute these things? And we have to start with a basic example, of course. All right? It starts with a formula, and that formula is not very complicated, although it looks like it's terribly complicated. X minus X bar is the fundamental component of it. Because if you're going to find a standard deviation, you're probably going to want to find a deviation to begin with. All right, so this is my deviation. Just that inner part of the function. Everything else we do here is for the purpose of standardizing it. All right. Now I have my list of X values. I'm going to need an X bar. It's a simple list of data. This one we're going to do by hand first. It's actually pretty easy to do this for a simple set of data. For a frequency table, it's a pain, so we'll do that all on the calculator. But we'll use the calculator to check this one too. All right. So to get my X bar, I want to take the sum. All right. So 5, 11, 14, 20, 28, it looks like. So X bar is going to be equal to 28 divided by the number of values in the data set. So 7 is equal to 4. So I now know my X bar value. Let me get a nice horizontal in here. I'm actually going to draw a column that contains only X bar. So I'm just going to rewrite the number 4 7 times. And the reality is this is the only time we're ever going to have to do standard deviation by hand. So just write the column with the 4s in it. Like, who cares? You're never going to have to do it again. I'm not even going to ask you to do it on a test or quiz. All right. It's more about evaluating what it means than anything else. So X minus poor quality X, undo. X minus X bar, so now you have an X and an X bar that you can subtract. 2 minus 4, negative 2. Negative 1, positive 2. Negative 1 again. Positive 2 again. 4, and then finally negative 4. Next up is X minus X bar squared. The idea behind this is, I'll call it the zero-sum conundrum. That's not even remotely what it's called, but it sounds fancy, and so most people go with it. The idea behind that is you can't always get a true sense of the deviation, the accumulation of deviation, the cumulative deviation among the x values from the mean, because some of the values are positive and some of them are negatives, and some of the positives offset with some of the negatives. So you don't get a true sense of the deviation. So there's two ways to handle that. One way would be to just drop all the negatives because the deviation is a distance. Another way to handle it would be to raise each of these values to an even power. All right. So this becomes more of a what came first, the chicken or the egg kind of paradox, because you don't necessarily know that squaring the values is the way to go until later in the course, where you find out that pretty much everything else, everything that comes after this in statistics is related to the standard deviation, which requires you to square the values. All right. So it actually turned out that all of the concepts that followed this kind of came first and helped us derive this method for standardizing those deviations. All right. So most people interpret that as, okay, so we just square it? Yes? Okay, that's what we'll do. A handful of people in the past have had the thought of like, well, what can we just drop the negatives? And so the answer to that is because statistics won't work the way we want it to if we do that. Right? So square them all, we drop the negatives. Unless you type it in the calculator incorrectly and don't really think about it, which happens more often than you would think. All right, so we have all those values, all positive. If you type this in your calculator, just be careful. When you're doing something like negative 2 squared, you shouldn't need a calculator for. But sometimes the numbers, you can get some funky decimals. And this is just, again, some of us are turning these calculators on for the first time ever today. If I typed in negative 2 squared and hit enter, it's going to tell me negative 4, which is incorrect. All right. Actually, it's correct based off what we typed in. This is saying negative 1 times 2 squared. All right. What you really mean is negative 2 in parentheses squared. All right, which is the positive 4. So very, very subtle thing, but it could cause you to get an answer and not really know why you got that incorrect answer. All right. So the numerator is telling us to add up all those values. So the sum of x minus x bar squared. We're just adding those values up. That's all there is to it. In your calculator or in your head, it doesn't matter. We have 32, 46, it looks like. 10, 16, 5, 10, 14. Yeah, I think so. All right. Then the bottom says n minus 1. All right. N is the number of values in a data set. In this case, n is equal to 7. So my s squared, which is the variance, which is not the standard deviation, but you got to get that before you can get the standard deviation, is 46 divided by 7. Welcome to leave that in fraction form if you want, or you can put it in decimal form. If you want a more precise standard deviation, you're better off leaving it in fraction form, because the next step is to take the square root of that, because s, 7 minus 1, thank you. So that would be 46 over 6. No need to simplify, because we're going to get a decimal final answer anyway. So s is equal to the square root of the variance. Which is the square root of 46 over 6. And that's where we get our approximate value. All right, so the square root of 46 over 6. I'm talking about 2.769 roughly. And so that's our standard deviation, our sample standard deviation. Now, in the next unit, we'll learn about population standard deviation. The only difference in computation is that you don't subtract the 1 in the bottom. All right. That being said, the real difference is that there is no difference whatsoever because we're going to do it all in the calculator from here on out. So let's type this data set in our calculators. First, to verify that we didn't just screw this up, which really would be all your fault, because I screw stuff up all the time. But when 30 people let me do it, that really makes it on you. Nah, you got to watch me like a hawk sometimes. My classic story is, and it had to do with this concept, standard deviation. The second example, I chose to do it by hand one semester. I screwed up the mean. Made a slight error with the mean. So if you recall, that was the first step. So we got like 25 minutes into the solution of the problem, and then a student said, oh, actually it wasn't even a student raising their hand. I was like, hey, let's check it on the calculator. The answer was wrong. And I said, dang, the answer was wrong. Then a student throws up a hand and says, oh yeah, I noticed you screwed up the mean in like the first step. And I was like, you noticed that 25 minutes ago and you didn't say anything? What the hell, you know? And so there's a classic balancing act of like, well, you're like a teacher. I thought you like knew the answer and stuff. So it was usually like I figured I screwed up somewhere, so I wasn't going to say anything and look like a schlemiel. So, you know, it is what it is. But if you see anything out of whack, like that -1, personally, I'd rather take the hit when I make the mistake, because I like the big reveal of like, all right, now let's check our answer with the calculator. Enter. See, it's exactly the same, as opposed to enter. All right, where the hell did I go wrong? All right, let's stare at this for the next 20 minutes, you know? So please tell me if you see anything, all right? So I don't take it personally. After 20 years of teaching, it's not possible to take anything personally anymore. So anyway, stat calc, 1 var stats. Now, this did not have a frequency list. This was only data that we typed in L1. So you want to hit clear on frequency list. All right, you want to blank that out. And then hit calculate. All right, so again, we have a lot of funky looking stuff here. We computed X bar, we got 4. Yeah. The 2363680. Yeah, no problem. All right. One thing I don't like about, I mean, there's a lot of things I don't like about the calculator, but it's like a necessary evil because it does so much that's, the good outweighs the bad. It says SX here, and we denote standard deviation with an S. So you might be like, well, is that the same thing? Well, we know it's the same thing because look, we got the same value. But aside from that, all the calculator is saying is S with a subscript of X, X representing the X values that you typed in. So S for those X's. All right, so when you think about it like that, it might start to make a little bit more sense. This other one here, this little sigma, lowercase sigma, that means population standard deviation. That's the second unit. All right, so just think unit 1, unit 2. You don't have to worry about this one yet. In the second unit, you have to worry about this one. You don't have to worry about this one. It'll be the reverse in the second unit. All right, so It's just the S at this point. So instead of taking you through, and this is the last thing we'll do for tonight, and then you'll be off the hook. Find the sample variance and sample standard deviation for the following data set. So stat, edit, wipe out the data that you have here, clean slate protocol. Movie reference, anyone? Which one? Very good. Very good. All right, so we got 10, 20, 35, 41, 52, 11, 14, 1, 3, 8. Double checking this way, that way, backwards, forwards, upside down, left and right. Okay. You just got to double and triple check. I try to, on a test, if things are slightly off, because I'll tell you right now, and I will give you the breakdown for what's going to be on the test question by question. Question 1 will be creating a frequency histogram. Question 2 will be creating a box. You know, you'll get that list. One of the questions is going to say find the mean, median, and mode, range, mid-range, standard deviation, variance, and it's related to a data set. You type the data set in incorrectly, you get all of those wrong. If I can find your mistake, it won't cost you much. If I can't find your mistake, it's going to cost you the world. All right, because that's what it is. You know, like if it's only slightly off, I'll be like, all right, you typed in something in, let me try to transpose a couple of values, maybe skip a value. I'll play around with it and see if I can come up with your numbers. But if I can't find your mistake, then there's really not much I can give you. All right, so that's how important this is. You've got to double, triple, quadruple check your work. All right. That being said, it's a whole lot better than having to do all this crap by hand. So always keep that in mind. Stat, calc, 1 var stats. Now I have a frequency list. All right, so frequency list, L2, second 2. And then calculate. So they're asking us for 2 things, sample variance and sample standard deviation. The calculator is giving us one, but not the other. All right, so the SX value, or just the S, is about, I'm going to write the approximate value here, but I'm going to caution you that in order to find, so this is a standard deviation, so S. In order to find the variance, we need to square this number, but you can't square the rounded value. All right, you have to square the more exact value, which means you need this whole shebang here. All right, I'll show you 2 ways to do it. One way is easier than the other. All right, so one way to do it would be to find the variance from the standard deviation. You just write that number down, the whole thing in its full glory, 16.230879, and so on. 25657. Then square it. All right, if you've already lost interest in that approach, I understand that. Some of us are like, well, simple and direct. It's not ideal, but I'm going to do it. Oh, okay. Okay, yeah, that's fine. That's fine, because I make answer keys with a variety of different calculators, so I'll do it with your calculator, everybody's calculator, and it'll all work out. All right. The other approach, okay, so you can type that in and square it. Last I checked for some of these calculators, the minute you start typing in, it blanks out the screen. So make sure you write it down first. Otherwise, you have to recompute, which is not a big deal. All right. Now, an alternative. And since you will have a note card for the first test, and most people choose that note card's 3 inches by 5 inches. You can't fit the entire unit on that note card, but what most people choose to do is put little calculator reminders on that note card. This might be one of them. SX, you can call that up in your home screen by going into the VARs menu. So I'll write that down. So VARs for variables. On your calculators, it's option 5 for statistics. And then you'll see the entry. It should be option 3. To call up the SX.
So it's
It's VARs, then option 5, which is statistics, and then option 3 is the one that says SX. And so that'll bring that right into your home screen. And so all you would have to do, so that brings SX into your home screen. All you have to do is square that number. And it'll compute it for you with the most unrounded form of that value. All right. So
it doesn't matter because mine was off by like 2 digits.
Yeah, it won't matter because it's in the calculator. It's stored the true value. It doesn't always display the same value between my calculator, your calculator, somebody else's, but stored within the calculator is a true value. And so then once we get this, we can round it to approximately 263.441. Now, you may get lucky. It happens sometimes. Maybe happens in this case. Let me try it with the rounded value, 231 squared. Oops, 16.231 squared. It may give you the same rounded. You see, it's a little bit off. All right? And I always think stats, like we're the grunts. The statisticians are the people behind the scenes. We're not decision makers with the data. We're just doing the math for the people who are making decisions. All right? So I don't know what this data is for. I don't know if that deviation from 0.441 to 0.445 is a big deal. So if somebody asks me to run the numbers on something, I'm going to give them the most accurate possible value. All right? So this value is more accurate than what I would get if I just squared that number. All right? So we use the true value. Now, if you take this whole shebiggity bang here and square it, you should get this one rounded. All right? If you don't, then definitely VARs 5.3. Question?
So when we get to VARs 5.3, what do we do after that, for the SX?
So you call up that SX. So you're in your home screen. So VARs, so you hit option 5 and then option 3. Then you hit the power of 2. So you're squaring it. So you're hitting this key. And then hit enter. And then it'll actually square your SX value. So it's a little recall feature. I mean, it's the closest the calculator has to copy paste.
Does it matter if you use the caret instead?
It doesn't matter, no.
263 is the variance?
263.441 is the variance, yeah. All right, and so you'll see on the test that there'll be a problem that says find the standard deviation and then find the variance. And so you're going to want to do it this way. You know, for us, it's a matter of, losing half a point if you screw it up. But in the real world, it could be more devastating. I'll give examples of that next class. Question?
And what's the significance of the variance again?
The significance of the variance is just another measure of variation. So it goes hand in hand with standard deviation. There are other statistical techniques that we're going to learn later in the course that actually relies on variance as opposed to standard deviation. But it still just gives a measure of how spread out the data are. And just like standard deviation, it's a comparative measure. The bigger the number, the more spread out the data are. The smaller, the closer to 0, the more tightly grouped the data are. All right, so that's where we're going to leave it for tonight. If you have any questions, stick around. Otherwise, have a wonderful evening, and I'll see you on Thursday. If you missed attendance, make sure you. Did that win the Academy Award?
Well, I think it was nominated.
It was what? Yeah, I remember it being a big deal. I don't remember it. Was that the year?
Oh, my mom's
Oh, the English patient, I think, won
Oh.
that year.
Yeah, it's the same woman, Julia Binoche.
Oh. I'll have to look. Yeah, I gotta check it out.
Pretty sure.
Yeah, so this focus group is for male children, so that's red flag right there, ages 7 and 8 who love chocolate in Westchester. All right, so it's like, okay, well, automatically you think scam. They're trying to kidnap my kid and hold it for ransom. So, like, it's like we want your child to be part of this.
Do you want some candy?
Yeah, exactly. Like, that's exactly what I thought about. I'm like, the whole focus group takes place in a white van with no windows. So, like, this is not a good thing. But the ad says we are looking for male children ages 7 and 8 who love and enjoy eating Kinder Joy chocolate. Your child must be outgoing and able to talk about why they really like and enjoy eating Kinder Joy. It's for 1 hour and 15 minutes, paying $125. And you know, these are the kind of things where you walk into the whatever the place is, the room, and if they say, okay, come back in 1 hour and 15 minutes, you're like, thanks for your time, come on, we're leaving. You know, but if they say you sit here and you could observe, you just got to keep your mouth shut, you know, like that's a different story, I guess. But yeah, it's like they have these specific criteria that they're talking about. You know, you got to be 7 and 8, between the ages of 7 and 8, and you have to love chocolate or Kinder Joy, and you have to be willing to discuss why you love it. Now that last little piece is so that they can get the information, you know, so the outgoing part, but it really kind of limits the conclusions that they can draw, because the only conclusion that you can really get out of that is that outgoing kids love Kinder Joy because of these reasons. You know, so what about the shy kids? You know, like, will they like Kinder Joy? I don't know. Well, you didn't allow those folks to be part of the group, and so if they're not part of the group, then they're not represented in the sample. So therefore, you can't conclude anything about the non-outgoing people in the population. All right, and so measures of position, measures of variation, measures of center, they're all going to kind of fall into place when analyzing data, so that you can actually draw those meaningful conclusions, but you do need to have a representative sample. All right. So every score in a data set can be represented in terms of standard deviations away from the mean. All right. So it's basically using the standard deviation as a ruler. You know, like you have a ruler. If you think about, you can visualize a ruler. It has tick marks on it. I wonder. Nah, it's a different app. I think I had an app that had a ruler on it. I don't think this is one of them. That's a lasso. Those are my lightsabers. Nah, yeah, it's a different app. But it just visualizes a ruler. It's got little tick marks on it. Each one of those tick marks would be valued at whatever the standard deviation is. All right, so instead of being 1 millimeter or a 1/16 of an inch, it would just be whatever you computed the standard deviation to be. That's what your ruler would be. All right, so that I suppose I could try to draw it. Anybody who's ever seen me draw before, though, knows that this is not going to end well. And I have like auto-correcting abilities. It's just I don't have any other artistic abilities. All right. Oof. 1, 2, 4. All right, I got 16 of them in there. That's what I wanted. 1, 2, 3, 4, 5, 6, 7. I'll make this one bigger. All right, so this would be 0, and this would be 1, 1/2. And then, you know, you can label everything up if you want, but really the idea is that each individual tick mark would be valued at 1/16, because the distance, it actually doesn't look half bad. But I'll take it as a typo. Include diagram of ruler. I talked to you about typos in this class? Okay, so that made no sense. All right. So 1/16 is my scale factor. All right. All right. So how does this translate to standard deviation? Well, you could have a ruler, another ruler, and it's too much of a pain to copy paste on this app, so I'm just going to try to draw it again. And then this time I'm just going to kind of move it. I'm just going to move it to the side a little bit. Now you could have, any number of little tick marks, but in this ruler, each tick mark is going to be a measure of the standard deviation. All right. So you'd start off with 0, and then you'd have 1 standard deviation, then you'd have 2 standard deviations, then 3 standard deviations, and so on. That's only in the positive direction. You could also go in a negative direction, which I'll get to in a minute because I'm going to draw a different diagram. But this tends to, in my experience, kind of sell the idea a little bit more than just jumping to the other diagram. So 1S, 2S, 3S, 4S. Be very careful because I've seen it way too many times before. Somebody will come up to me before the test and say, I understand everything in this unit. I don't know where the 15, 25, 35, and 45 came from. Can you explain that? Like those are S's. Right? So make them look like S's. My handwriting is garbage, so I do what I can. Right? But 1S is 1 times S. Just like if I went 2/16, that would be 2 of the 1/16, or 2 times 1/16. All right, so each one of these is a multiplication problem, I guess, or question, or request, requirement, etc. Lots of different ways I can frame that. So you put a little multiplication symbol in between if you want. If you're comfortable enough with algebraic notation, then you wouldn't need to do that because you know that a number adjacent to a letter is the same as multiplication. All right, but if you need the reminder, just pop it in there. And so with that in mind, I could, 0 really isn't 0 anymore. It's 0 times S. All right, so what's happening in our little empirical rule, which is what this whole blurb here is referring to, is telling us that if you're going to have what's known as a normal distribution, which is a bell-shaped curve, or at least it starts off as a bell-shaped curve, about 68% of the data has to live within 1 standard deviation of the mean, about 95% within 2 standard deviations, and about 99.7 within 3 standard deviations of the mean. The approximate symbol, we define that to mean plus or minus 2% roughly. Right? You're going to find that statistics is a kind of a wishy-washy branch of mathematics because there are a lot of about, or approximately, or give or take, or in the neighborhood of, or roughly. All right? Those terms, they don't sit right in a math class where x equals something. Now x is in the neighborhood of something, and it just doesn't quite feel right. But our thought process here should be more in the realm of trying to disprove relationships rather than to prove them, right? Because, like, for example, if my classic example is you talk about the average height of the human race. Like, I can't prove that that's a particular number. Okay? I can't say that the average height of the human race is 5 feet 4 inches. Like, if you try to pin me down on a number, I'm going to get it wrong because somebody could disprove it. All right, so with that in mind, I can use my knowledge of statistics to refute somebody else's claim. So if somebody said the average height of the human race is 5 feet 4 inches, I can collect a data set and prove them wrong. Now, somebody else can collect a data set and prove them wrong, but in a different way. Maybe I'll prove them wrong because they have an overestimate. You know, their number's too high. Somebody else could come up with a data set that gives evidence that their number is too low, right? But I guarantee you, it's going to be a pretty rare instance where you collect a data set sufficiently large that you're going to hit that number precisely, right? And so we're looking at confidence. We're looking at the idea of rarity and the opposite of that, right? And so this is the foundation of all that stuff. So our first job is to visually determine whether the following distribution is normal. Well, that's kind of a tricky proposition because we haven't learned statistical graphs yet. But if a distribution is going to be bell-shaped, it should be roughly symmetrical. All right, so here's what a bell-shaped graph would look like, roughly. All right, and it should have some symmetry. All right, roughly. Should be roughly symmetrical and roughly bell-shaped. Approximately, roughly, same thing. All right, so you can look at a raw data set and get a sense of whether or not that's the case, because each of these frequency values represent the counts of these numbers. All right. So what this is telling me is that as I work my way away from the center of the data, right, so here's my center, 18, 20-ish. It's organized in increasing order, so it's a strong case that this is the center. As I work my way away from that, the counts should get smaller and smaller, with the largest in the center. All right, so I'm kind of looking at it sideways. I'm looking at this as, okay, this is where the most data are, or is, corresponds with the center of this graph. And as I work my way outward, it seems to feather out. It seems to get less and less, just like the graph does. Right? And we'll learn how to create these graphs precisely in a little while. But for now, that's all we need. Seems to be approximately normal. Because most values are in the center, and the least number of values are on the fringes. Or you could say the data, the amount of data decreases as you move away from the center. There's a lot of different ways you can phrase that. This is just the way I chose to. There aren't really that many requirements when it comes to explanations. Just the idea is that if it makes sense, if it's reasonable, and it embodies all the characteristics of the problem, then you're in good shape. Right? The next part, then verify using the empirical rule. Well, that's a different story. Now we got to do some math. All right, math is fun. In order to do this, you can see here keywords: standard deviation, mean. We need those two pieces of information. Yeah, it's pretty good. Almost full. Thank you. All right, so we got to pop this data in our calculators and run one bar stats. All right, let me get my cal. So go up to the column heading, hit clear and enter. Same thing for the second column. Doing a quick double check. As we know, that's the number one way of screwing all this up. All right, so quit out of there, just so you don't accidentally type a command into a cell. You're gonna do stat calc 1. It's a frequency table, so we need list 1, L1, and L2. Now, does this work like that? No. Let's do it this way. And hit calculate. And all I need is the mean and standard deviation, so I'm in good shape here. I'm just gonna put these images in there. Oh, you know what? Pause. I'm just gonna go ahead and not have nerve damage anymore. Just not do that. It's easier that way. So anyway, here's my values. Now, I wanted to have this on the screen because we need to make 3 calculations when it comes to applying the empirical rule. One is that we have to compute x bar plus or minus 1 times s. All right. So x bar plus or minus 1 times s. We also have to do it for 2s and 3s also. So I'm just going to jot it all down. All right. Now you want to try to let the calculator do this for you. All right? You don't want to have to do it by hand. I mean, you can. You got the numbers right there, but then you have to work with the most exact values. Which means if you're doing it by quote unquote hand, you'd have to account for every one of these decimal values until you get to the final step. You don't want to deal with that. All right? So what you do is you go into the bars menu, look for option 5, which is statistics. And then you'll see your option 2 and option 3 are there. All right, so bars, almost fell. Option 5. You want 2 and 3. A little different on my calculator, so I'm writing it out here instead of doing a screen grab. All right, so once the calculator computes what the x bar and s, the sx, if you want, you make these sx's so it's consistent with your calculator. It means the same thing because we talked about it last time. S of the x values, right? It makes sense. All right, so in your home screen, clear out all the garbage. Vars option 5 is 2 for me for some reason. Then option 2, bring up the x bar. Then what I do is I do the minus first. Then I type in the 1. Even though 1 times anything is not going to change that anything, I put it in anyway. Times, it's a ridiculous looking multiplication symbol on mine, but it should look fine on yours. All right. Then vars. So again, vars option 5, statistics, and then you're finding sx. So you're only going to be able to do the subtraction and the addition separately from one another. All right. So enter. You're going to get the lower bound of the interval. All right. So this you could round, 16.686 approximately. All right, we put hard brackets around it. And then comma. So what we're going to get a result that looks an awful lot like what we did for outliers. All right. And that's fine because there's going to be some familiarity with that. So why did I do this in such painstaking detail? Well, so now I can hit, and this step works for all the calculators. Some of the older calculators won't be able to, you could scroll up on the newer ones. Second enter, oldie but goodie, brings up the previous entry. Now I'm just going to go back before the minus sign, hit delete, change that minus to a plus. All right. Sorry, second. Wait, does it overwrite? I'm getting my apps confused. Does it overwrite?
Mine don't.
Does it? Yep. If it overwrites, then don't hit delete. If you already hit delete, then I'll show you how to handle it. Besides, the calculator skills are things that you're going to want to get a handle on. I mean, we're, what, 3-4 classes in, and we've already, like, used some pretty advanced features in the calculator, and it's going to get even better or worse, depending on where you're sitting. Yeah, so it'll overwrite. All right, so if you deleted the minus sign, the opposite of delete is insert. So right above delete, you see INS. So all you would do is just hit second delete, and that allows you to tuck a value in there. You can just insert it right in. So the high bound is going to be about 20.973. All right. And we're doing this so that we don't have to do the calculations by hand. Now, you might look at it and say, but it's not a hard calculation to do by hand. All I'm doing is taking the x bar and subtracting from it the sx. But you're not writing all the decimal values. You don't have to deal with that. All right? If you ignored that, if you rounded your x bar and your sx, you're creating an unacceptable amount of variation in your answer. And that could, well, student perspective, it's going to cost you points, or could. From a statistical standpoint, it could be the end of the world. Question?
Yes. How did you get to the addition sign?
So what I did, let me just, I'm going to do the process again. So we did vars, we went into stats, I selected x bar, and I had the -1 times vars stats sx. All right, so hit enter, you get that first value. Second enter will bring up that previous calculation. Now on your calculators, you just scroll back, and your cursor is going to hover. You can overwrite the value. So you bring the cursor, put it right on the minus sign, and it'll allow you to first time for everything. So anyway, yeah, you can just change the minus to a plus. All right, but I have to delete it and then insert it. So. Sorry? I always do, because my interval is always going to have the lower number than the higher number, and the subtraction is going to give us that. Is that what you're going to ask?
Yeah.
Okay, cool. All right. I'm just going to check to see something real quick. I try not to cast judgment. There could be like a, hey, you know, I sent you a remind message, so you had to leave early or something. Or what are you gonna do? There's also the possibility, I don't know, I didn't recognize him, so maybe he sat in the wrong class for 40 minutes and just realized it. It's also, that's possible. That has happened before. Most people figure it out before 40 minutes have passed. So, I don't know. Sorry, you got. Oh, yeah. Now what I'm going to do is I'm going to hit second enter and change my +1 into a -2. I have to do it the old-fashioned way. Actually, let me do the 2. So if you hit second enter, you're just overwriting the +1 with a -2. And you'll get this value once you hit enter. That's always a weird conversation to have with someone. They're like, I didn't get what you got. You know you have to hit enter, right? Right, and yeah, if you're not familiar with the calculators, there's certain things that are intuitive for other devices. This calculator really isn't that intuitive. So, you know, if you're in doubt, just ask, because odds are you probably hit one of those quirky things. So again, second enter, make your minus into a plus. And I just realized after all that mine overwrites it too. Schlemiel. 23.117. Second enter. Minus 3 instead of the plus 2. You got the 12.398. Second enter. Minus becomes a plus. 25.260. Or just 26. All right, I'm going to get rid of this for a minute. All right, so those are our computations. We still have to do something with that. So we go back to the original data set, and we just start counting values. Right? Because what I'm looking for is the number of values in the data set in total, which I get from here. My display told me that, but you didn't do a screenshot of your display when you figured out the mean and standard deviation, so you might not have access to this. It's really just the sum of the F values. So if you add up your F values, you'd get that N anyway, right? So we have that. We're looking for percentages. So we're looking for the percent of values that fall in each of these intervals. Right? So I'm just looking at X values specifically. Each one of these are going to be out of 41. I'm just going to ask myself as I go down my list of X values, does this number fall in that interval? Yes or no? Does this number fall in that interval? Yes or no? And once I go through all the values, I'll start counting up how many there are of each of them. Right? So for the first one, 16.686 is my low number. Well, 14 is not bigger than 16.686. Neither is 16. Just barely not big enough. All right? The first value that's good to go is 18. 20 fits in that interval. It's not bigger than 20.973, but 22 and 24 are. All right, so this is my first interval. There are 27 values here, because all I'm doing is taking the sum of these two numbers. All right, because again, the frequencies are how often a value occurs. All right, so this is telling me that the number 18 is written out 14 times. The number 20 is written out 13 times. So there's a total of 27 values that are either 18 or 20. All right, so what I want to do is just make a note of that, not with that stray mark, that's going to be 27 out of 41. All right. Then I'm going to do the same thing. So in the X bar plus or minus 2s, X, I'm just going to ask myself, working from the top of the list to the bottom in terms of X, what numbers either do or do not fall in that interval? Well, the lowest number I have available is 14.5-ish. All right. 14 is not big enough. 16 is good. 18 is good. 20 is good. 22 is good because it just can't be bigger than the 23.117. But 24 is too big because it falls outside that interval. All right. A lot of stuff that you do in math really is a lot more simple than maybe we make it seem, just because we use words that kind of overcomplicate things like domain and range and stuff like that. everything kind of boils down to a glorified number line. Okay, so my ruler over there. So if I have a number line, the benchmarks on that number line would be the 16.686, the 20.973, the 14.542, well, that would be on this side, the 23.117, you can go a little bit south over here, the 12.398, and the 25.26. All right, so the numbers that we have in the table, 14, 16, 18, and so on, they're going to fall in this number line somewhere. So the 14 is going to be about right here. The 16 is going to be about right here. The 18 about right here. The 20 about right here. 22 about right here. And 24 somewhere over here. All right, all you're doing is comparing the numbers in the table to the numbers that we came up with. Right, and just seeing which ones fall in which intervals. All right, so the first interval was the 16 to 20 interval. All right, so that would be, 16 to 20. So that would be this. You see, it's only capturing the 18 and the 20. All right, the next one captures more. The next interval captures the 16, 18, 20, and 22. And the last one captures everything. All right, so it really is just a number line, but it's, you know, it's college level statistics class. We can't make it sound too easy, because then everybody will take the class.
You have to draw that?
No, that's for instruction. All right, so what we have here is 27 values and then another 12, so that's a total of 39. So I can make a note. And the last interval contains everything, all 41 values. Poor quality 41. Didn't get much better. All right, so what I want to do here is convert these values to percentages. Spot on, or they're going to be a little off, or they're going to be a lot off. So 27 over 41, about 65.8. Question?
The 39, you got that from the 27 and the 5?
I got it from the 27, the 5, and the 7. No problem. So we're talking about 0.659. 39.1 is about 0.951, and 41 out of 41 is 1. All right, so this is about 65.9%, about 95.1%, and well, 1 is everything, is 100%. All right, so the magic numbers are 68, 95, and 99.7. You can see that in the blurb up there. I got to be within 2 percentage points, roughly. So what I'm going to say here is that this is very close to being a normal distribution. Right, and that 65.9 is very borderline. And honestly, I mean, you could have situations where you only have to do the first calculation, because if it fails for one standard deviation, then it's all over. It's got to work for all 3 cases. If it fails for any one of them, then you just stop. All right, the one that it's most likely going to fail for would be the first standard deviation, right? Because I mean, you go out far enough, you're going to capture all the data, right? 68%, give or take 2 percentage points, that should put you in the 66 to 70 range. 65.9, that's right on the edge, depending on how you round. If you round it to the nearest percent, it's fine. If you don't, it's not fine. So we wouldn't say it's approximately normal. We wouldn't say it's normal. You never say it's normal, right? If you say that something is a normal distribution, you're absolutely wrong, right? Nothing is ever normal because that would be a perfect fit, and perfection in real life is not possible, right? So what we do is we just say it's very close to being a normal distribution. I mean, if you want to get silly about it, you could say very close to being approximately a normal distribution, but that's a mouthful. And also, it's like saying it's approximately a normal distribution. Approximately an approximation of a normal distribution. It's just stupid.
So this was a question, and we got 65.9.
You can go either way with it.
Yeah.
Yeah, and I think hopefully you're reading me right and saying, okay, so the way I'm going to go is to say it's not a normal distribution, so I have less work to do. Okay, all right, we're on the same page. Yeah. I'm also going to show you another way to do this so that at a minimum you can have a way of knowing going in what the answer is supposed to be. You know, I mean, there's one thing to draw the graph. Oh, look, it looks like a bell shape. I'm sure it's all going to work out. But there's a very, very streamlined approach that'll just give you the answer like that. And then you just have to kind of know to construct your work to support that. Right? So it ends up being pretty easy.